After some careful consideration, I've decided that rather than diving into a conversation about services, we need to look a little bit closer at this idea of networking and how our networks are actually going to put together. And there's no better way to be able to do that than to simply explore the functions of networking. Now, in the confines of building networks, what we do is we find ourselves embracing a number of elements. The first part is what is a network? Well, for the purposes of our conversation, we'll define a network as a group of devices, and we'll clarify what those devices are very shortly, but a group of devices interconnected such that they can communicate, and all of those devices are under one administrative domain of control. So in other words, I'm in charge of them. Whether I'm talking about this headquarters office over here, where the head office is actually connected to switches involving firewalls, routers, devices, PDAs, wireless devices, all of those individual components represent a network. But what we have to recognize too here is that as CCNAs, we have to be able to demonstrate that we have a firm understanding not only of what happens within our network, but also what happens between networks. Take into account the remote office up here. The remote office has its own switch, it has its own router, it has its own firewall, has its own internet access, has its own possible networking range. And what we need to recognize is that as administrators, even as CCNAs, we have to understand what's involved in this little device right here, the cloud, the internetwork, what we'll refer to as our WAN connectivity, our wide area networking interconnections, which afford us not just the idea of networking, but also a concept of internet working. Internetworking being communication between networks. So, the definition of a network for the purposes of our conversation is multiple folds. We have the network, which is going to be a single individual device, which is what we're going to be focusing on in ICND1, building a small serviceable network, affording that network access to the internet. And then later on in ICND2, interconnection of network devices, part 2, we're going to talk about being able to employ routing technologies in order to be able to communicate between sites. So we can see here very quickly that this could get really complicated. In other words, we need to understand what goes into creating a network, and we are going to be able to find no better way to explore that than discussing the components of a network. Now, the components of a network translate to a number of things. For instance, we can see right here I have a router. Now, a router traditionally is going to be illustrated as that hockey puck that we talked about earlier. But what I wanted to do is I wanted to divorce the graphical representations for equipment to three-dimensional images that are going to be a little bit easier for us to visualize, because when we start looking at this, what we need to recognize first of all is we need a firm understanding of what each of these devices do and the services that they provide. Now, in a nutshell, we have two key networking components: our routers and our switches. Now, if I have a network, I want to connect all of the devices on that network to a switch. Now, I can connect multiple switches together and daisy chain them such that I can have one large domain. And later on, we'll talk about a concept called virtual local area networks. But right now, let's just assume that a network are going to be devices that are connected to the same switch. Now, if I want to be able to communicate, let's say I'll take myself out of the equation here. If I wanted to be able to communicate from here to here, so between PC A to laptop B, what I have to do is I have to understand exactly what happens here. Because notice, at a fundamental level, let me grab a red pen. At a fundamental level, there's no connectivity directly between these switches. So my traffic is going to go up to the switch, and it's going to look for an avenue to be able to get to here. And it can't find one. So ultimately what it's going to do is it's going to get sent to the router, and the router will then route it between networks. So for the purposes of our conversations, what we see right here is this is going to be network A. This would be network B. And therein lies our recipe. Therein lies the answer to our question with regard to the capability of devices. Switches provide network connectivity. So I have devices that are on the same network. They're going to be connected to switches that are in that same network. If I want to communicate from network A to network B, I have to employ the services of a router or some type of routing capable device. Now, when we start talking about the OSI model here shortly, what we're going to find out here is that devices operate at different levels in our networking infrastructure, our design. The OSI model is a set of rules or governances that the industry standards bodies have put together so that when IBM makes a networking device and HP makes a networking device and Cisco makes a networking device, those devices are going to be able to intercommunicate and interoperate because they both follow the rules of the international standards bodies open systems interconnection model topology or outline, the OSI model. Now, keeping in mind, like I said, switches are normally for network communications. Routers are going to be to communicate between networks. So if I want to be able to build a network and get to the internet is one big internetwork. So if I have interconnectivity, even in a small configuration over here, notice in this one setup I have PCA and a printer and a switch. Doesn't get much smaller than that. It's two primary devices with a networking device. Well, the moment that I connect that to a router, I could go to another site, or I could also connect to the internet at large. So keeping in mind the fact that even our small networks are going to have some internetworking components in order to be able to communicate to the outside world. Now, other components that we see here is, for instance, I've got a bank of servers. Right here, I've got a laptop. Here, I've got an IP telephone. I even have a PDA up here that's using some wireless technology. I have clients where the moment the client walks into their office, their telephone connects to the network and their iPhone or their BlackBerry, their BlackBerry connects directly to the enterprise and it becomes a networking asset. We have printers. We have other devices that aren't part of this drawing. We have storage arrays where we're going to be able to have network attached or storage area networks such that we can save vast amounts of information to devices located on the network. And we're also going to find out that we also are going to, more often than not, have those locally replicated, as well as possibly, and let me go ahead and change pin colors here, as well as having them replicated between sites. So if I were to lose communication, what I would want to be able to do is if I lose one of these devices, I'm okay. If I lose both of these devices, I can still come over here to the other data center or to the other site via my router in order to be able to access the information because I may be and probably are running some type of replication services. Now again, we'll talk about services in more depth later. Right now what I want to do is I want to keep delving into this idea of what exactly goes into networking and how networking is going to operate for us. Let me go ahead and grab my eraser right here to see if I can get rid of. Bear with me just one moment. One moment here, I apologize. Ended up on a slide I didn't want to be on, trying to erase something. Okay, let me see if I can get this to erase real quick. There we go. So, what goes into creating a network? Exactly what we talked about, all of those components. But the other part of this is we also have to understand that in order to be able to find reason in all this, we need some type of graphical representation of the network, something referred to as a network diagram, and that's what we have up here. Now there's some elements that are missing out of it with regard to how things are connected, because when it comes to things like wireless laptops or the wireless PDAs or the BlackBerries, what we're going to look at here is the fact that we don't have a physical connection between them because they're using RF radiation to be able to communicate. But I do want to make certain that we're aware that they exist. So when I look at this drawing, what I'm going to do is I'm going to need to extrapolate where or how things are interconnected. So just from a 30,000 foot view, we see we have a router. Again, would be represented by that hockey puck. We have a switch. And what we have is on each of these devices, we have a series of ports. For instance, here, let's assume we have two physical ports. This port may be Fast Ethernet 00. This one may be Fast Ethernet 01. Now, Fast Ethernet 00 is going to be on a physical Ethernet cable connected to this switch. Let's just say for the purposes of our conversation, this is going to be SW1 for switch 1. Now, the moment we connect to that, we have to recognize the fact that we're going to connect to a physical interface. This may be Fast Ethernet 024, depending on how many ports we have on our switch. There are also going to be other connections. So let's say Fast Ethernet 01 connects to this laptop's network card. Well, the moment we start looking at this, this drawing now becomes more and more useful for us because it's showing us exactly what is connected to where and how. And this becomes really important because we may have situations where, let's say, we have these servers. Bear with me one moment here. I'm having problems with this highlighter. We may be having a situation where we have a server here. And this server is hosting a web page, www. And I want entities from the outside world to be able to come through the network, through my firewall, and connect to the server to be able to view web pages. I may have a situation in my infrastructure where this is not happening. So when I look at this drawing, I know I have different devices that could be involved in the problem. So it could be my firewall. It could be a problem with my router. It could be a physical or logical issue associated with my switch. It could even be on my server where I have my actual problems. But it's going to be through the graphical representation of what's happening to our network and how our network is interconnected that we're going to be able to turn to be able to help isolate or to minimize the amount of time that it may take to find a problem. Also, having a firm understanding of how to interpret a network drawing or a network diagram is going to allow us to better do our jobs. And also, you're going to find yourself in many times where you have no drawing, where you have no network diagram, and you're going to want to know how to create one. And you're going to need to know how to represent it in a logical fashion such that another person can come in and see exactly what it is you're illustrating and it all makes sense to them. Now, networks are very interesting because they're not straight, unchanging entities. Networks constantly evolve and mature and change over time. And we also have to recognize the fact that they're used for different things. So in the confines of what we've been talking about right now, it's been all physical components, all physical elements, printers, routers, switches, computers, PDAs, IP telephones, anything that we can connect to a wire or run through an RF radiation connection to a wireless device can be a component on our network. I think of it like my sons playing with Legos. They have red Legos, blue Legos, white Legos. They have orange ones, they have green ones. And they can build all of these structures by using each of those individual components, those different colored Legos. And that's what we're looking at here. We're putting together a network by using devices or components, and we're assembling it in a very similar fashion to the way my sons use their Legos. Now, what we also have to recognize here is that we have issues. Issues involving how information moves through our infrastructure. So how are we moving information throughout our infrastructure? Well, when it comes to moving information, what we have to recognize is that there are three main categories of interaction. The three main categories are batch applications, interactive applications, and real-time applications. Now, the way I want you to think of a batch application would be a machine talking to another machine via the network. So they're moving information back and forth. This could be things like file transfer protocol, trivial file transfer protocol, inventory updates, storage synchronization. Remember I drew that illustration of how my different devices could be connected to one another? Well, in this scenario, let's imagine that I have two storage arrays that are connected to each other, and I'm backing one up to the other and vice versa. So they're actually moving information back and forth for the purposes of synchronization. Well, in this scenario, these two devices are talking to each other. There is no direct human interaction in this type of involvement. Bandwidth is important because the more bandwidth that I have between these devices, the faster I can move information, but it's not critical. And 9 times out of 10, I'm just going to guarantee you that one of these two computers is not going to call their boss and say the network's slow and you're going to get in trouble or at least called on the carpet. That's the beauty of between these machine-to-machine or these batch application processes. And it's going to be probably things that happen at night in many times, like for instance, backing up information to tape drive, synchronizing your storage arrays if you do have a storage area network, that type of thing. Now the other part of this is the fact that we need to recognize that not everything is quite as pure as this. We have scenarios where we have people that have to interact with machines. And that happens a lot more than the other. And in this situation, this human-to-machine interaction is two-way. And we have to recognize something else here. And that is the fact that our users normally will accept a specific level of problematic behavior. Now, what do I mean by that? Well, in the terms of networking, we have a vocabulary word called latency. Latency represents how slow or how fast the network is into providing responses to queries. Whether that's moving information, whether that's querying a database is irrelevant. The latency is the amount of time that the student or the person is waiting. Now, as long as the latency is acceptable and consistent, the majority of our users won't complain. And that's why this interactive applications model is as useful as it is. And now notice right here, it does tell us, it's like bandwidth, again, is important but not critical unless the wait becomes excessive. That's when the guy's picking up the telephone, he's calling his boss, who's going to call your boss, who's going to call you. Now, we want to be able to avoid these scenarios when and where possible. And we need to be able to employ methods and techniques to do that. When you're studying for your CCNP, you're going to talk about things like quality of service mechanisms. Ideas where you can take one particular type of traffic and give it preferential treatment over all of the other types of traffic on the infrastructure. You can even do it to the detriment of all of the others, but you still have the capability. The key thing to remember here is quality of service, QoS, does not give us more bandwidth. All it does is allow us to more, I won't say even efficiently, more directly or more granularly manage the bandwidth that we currently have. It does not give us more bandwidth. It can't make a link faster. Only money can do that. And we're going to talk very shortly about some of the characteristics of networking, and cost is one of them. Now, in this scenario where I have the person waiting in front of the machine, latency is going to be important. So if it's not excessive, the user he'll probably grouse at the water cooler, but he's not going to go so far as to escalate a problem or a trouble ticket. Where the last scenario, this is going to probably be the most problematic scenario that we can run into in the confines of building a network. And that's going to be when I have a person-to-person. There's no machine, but I have two people interacting with each other in real time. At this particular juncture, high latency is a problem. But it's not just the latency like we described in the human-to-machine interaction or the interactive applications. Interactive applications, that communication was pretty much two-way, but nowhere near as bidirectional as two streams of conversation. In this scenario where I'm talking about real-time applications, I'm talking about VoIP and video. Those are the most common apps that we're going to run into in our infrastructure, and we need to know how to embrace them, and we also need to recognize early on the possible problems that we can run into when we do have them operating in our network, because they can be the most problematic with regard to user complaint. And also we have to take into account things like latency is going to be more end-to-end latency, and it is exceedingly critical. So any issues or any problems that we run into in the network can manifest in user complaints very, very quickly the further we move down this list. The tape drive's not going to complain that it got a slow response from the server. However, an interactive application where a user is trying to recover data stored on a tape drive, thereby you may find some complaints. But as long as they can get that data, more often than not, the user is going to be happy. But it's down here when we're sending information in these real-time applications like video and telephony that we're going to have the majority of the possibility, the greater possibility of users complaining and impacting us as network engineers. So those are all very, very important. And when we look at it, like I said, networks really boil down to some key characteristics. Among them, the primary element from two different points of view. First, speed. Users are all about speed. The business managers or the financial guys are all worried about cost. And the key thing that you need to understand here is that speed comes at a cost. All of these come at a cost. Security adds cost to our infrastructure. Availability, i.e. making certain that something is highly available, is going to be assigned or part of a cost. Scalability, the ability to be able to expand or grow our infrastructure, again, is going to directly correspond to cost. And reliability, because anytime I use the term reliability in networking, I'm talking about 2 or 3 of the same components. So instead of 1 web server, we now have 2. And that's going to be a direct correspondence to cost. And topology. Topology is really something that only makes sense to us network guys. But when we look at this, these are going to be the terms under which we are going to be describing our network. So they're considered to be the fundamental characteristics behind networking. So when you're talking to your boss, you're not talking topology. You're talking speed and cost. So the boss is going to ask, well, how much speed can I get at what cost? So what's the maximum amount speed I can get at the lowest amount of cost? The boss comes back and says the server died and it cost me a small fortune yesterday, and we weren't able to process our online orders for our e-commerce. And that's because you turn around and say, well, you said that you didn't want us to have a second system in tandem for failover in case something happens. So we have a less availability, or a lower possibility of high availability to our users. And at that point, that's when everyone starts understanding that these terms are both real and ethereal. So the idea of cost is going to be the actual capital investment required to buy a server. It's also going to be the operational expense associated with paying our salary to maintain those servers. And sometimes that value seems astronomical until one of those servers dies and we have no high availability, and then the business starts actually losing money. So the money lost in comparison to the money saved is normally disproportionate. But these are going to be the values that we're going to use more often than not to discuss our networking, our network aspects in terms of services and capabilities. Now the other part of this is that we have to recognize the fact that we can hook up these devices in different fashions and different ways. So when it comes to deploying the majority of these interconnections, the most logical one that we're going to have is going to be this one, which is the star topology and the mesh topology. Now, I don't like the representation here of the mesh topology because technically there are 4. There's going to be the bus topology, the star topology, which is the most common. But when it comes to WAN deployments, it's going to either be the full mesh or the partial mesh. Now the reason we have the partial mesh here, which is what, notice not every device is not interconnected to every other device. However, there's enough replication of paths in this particular topology such that an individual link failure, let's assume, let me grab a red pen here. Let's assume this link right here failed and I want to communicate to this device. Notice I have different ways that I could go down to get to that device. And we'll talk about how we can recover from this type of failure, and this is going to be more involving with routing. But if we had a full mesh topology, that means that we would be absolutely bulletproof with regard to a link failure. There may be circumstances in a partial mesh topology where an individual link failure could black hole traffic going to a particular portion of our network. But the drawback to a full mesh topology versus what we see here, a partial mesh, and I'm going to go ahead and grab my eraser and take these off, is the fact that a partial mesh is cheaper than a full mesh. So if I wanted to be able to interconnect my remote sites using something like Metro Ethernet, I could have, for instance, from this connection to here, to here, to here, to here, to here, on every device. But the problem is that that's going to be a lot of extraneous cost for links that may or may not be used, or may only be used in the event of failover. So we as administrators or as network engineers find ourselves more often than not trying to create what we're going to consider to be the most resilient partial mesh configuration available to us. And that's going to be typically where the headquarters is multi-home to different sites, and then other key sites may have other ways to be able to connect. But from a point of view of being failure-proof, full mesh is the solution, but in most deployments, you rarely ever find a full mesh topology. In the confines of a star topology, what we see here is the star topology allows us to be able to illustrate the perfect deployment of a switch. Think of this as our switch in the middle, and all of our PCs or hosts, our servers, our printers, our routers, our PDAs, our iPhones, our IP phones, all interconnected to the central device in the star topology, which is ordinarily going to be a switch. Now, there are WAN topologies that meet this requirement. One of them is going to be a concept called DMVPN, Dynamic Multipoint VPN, where I can have all of my individual sites interconnected. And the cool part about that is that if we use DMVPN, what ends up happening is I can actually dynamically create spoke communications between each of these individual sites without having to necessarily transport the hub. Now, the reason I'm doing this is that I'm illustrating a point, and that point is that just like addressing could be physical and logical, these topologies can be physical and logical too. So in other words, this topology right here is a physical star topology, but from the point of view of its operation, it's a logical bus, because it's representing one Ethernet segment. So all of these devices, if this is a switch, would be on the same Ethernet segment. We haven't talked about VLANs yet, and we will talk about those, but the main thing that we want to recognize here is that it's through this interconnection that we have the capability of having the minimum amount of wiring, the simplest amount of management, but at the end of the day, it's still just a logical bus topology. And the whole idea here is a star topology is in effect a type of partial mesh topology logically. But when we start looking at this, remember, from my recommendation is to memorize this as bus, star, partial mesh, and full mesh, even though you rarely will encounter a full mesh topology. In the real world, it's still good to know that it exists. Now, the last part of this is logical topologies. Well, Terry, what's a logical topology? Well, a logical topology is just like a logical address. It can change. But in the confines of networking, the way we're going to define the logical topology is it's going to be the path that the data follows. So if I step back and take myself out of the equation here, notice that we have these computers right here. Bear with me 1 second here. We have these computers right here. They're all interconnected. Now, what we see here is, notice it's a ring of interconnectivity, but in reality, what we're going to find here is that we're going to have a switch. That switch is going to be connected in a star topology. So that's its physical layout. But from this user's point of view, looking at this user, they don't see the switch. We employ technology that's referred to as transparent bridging. Transparent bridging is exactly the term. The switching takes place and it's invisible to the users. So from a logical point of view, this user thinks that he has a direct connection to all of these individual devices, ignoring the fact that he's utilizing the switch to accomplish that, because the switch is not part of or an idea of what he sees. Now over here on the other side of the equation, notice here we have a bus. This is a bus topology, but it's a logical bus. Because, well, again, what's not drawn here is the fact that there's going to be a switch. The switch is part of the physical topology, but these devices don't communicate with the switch. They communicate directly with each other. So what ends up happening is they ignore the switch because it is transparent to their operations. Now, recognizing this, logical topologies play directly into the scenario. And what we see is the logical topology is the logical path. It's the logical path that the signals use to travel from one point on the network to another. Now, if we were to look at this, just from the point of view of trying to understand this as a physical device, this would look like this server would have 3 Ethernet ports on it. When in all actual fact, it's probably directly connected to the printer, but it's also going to be individually connected to a switch. So again, don't get logical and physical confused. And it's not going to be hard, but the main thing that you need to recognize here is that we find scenarios. I'm going to cut over to the whiteboard just for a moment. We find ourselves looking at scenarios where we have to pay attention to what's happening to our infrastructure. So let's bring up a whiteboard. Now, in the confines of what I'm talking about is this. I may have R1. R1 could be connected to R2 via Fast Ethernet 00 and Fast Ethernet 00 on both sides. This is a logical drawing. It's a logical drawing because we have to recognize almost immediately that these devices would never be connected directly. R1 customarily would be connected to a switch. R2 customarily would be connected to another switch. It could be connected to the same switch, but what I'm trying to do is outline the difference between logical versus physical. So now what we also I may have switch 2 in here. So switch 1, switch 2, switch 3, these devices could be interconnected, and it would be fast Ethernet 00 to fast Ethernet 01 here. Then it would be fast Ethernet 0, let's say 19 to 19. Let's say 20, 020 to 20. And then 02 to 00. That would be my physical connections. And it's through this idea of recognizing exactly the differences that we have to understand that our drawings that we're going to create have two different forms. We can have a logical drawing and we can have a physical drawing. From an administrative point of view, looking at data traveling across our infrastructure, if we make the assumption that our layer 2 is operational and working, then we really don't have to worry about the physical drawing, and more often than not we represent our interconnectivity in our illustrations using our logical drawings or a logical topology. We just have to recognize that for every physical topology, for every logical topology, there may be an underlying physical topology that is not the same as the logical topology. That's the main thing that I want to make certain that we understand. Now, with that being said, we're going to wrap this particular lesson up and move on to the other. I'll see you guys in the next portion of the presentation. Bye-bye.